Okay, so I guess this has been a very busy last couple of weeks for you. So there will be, so I'm here to, it's a sort of a bonus talk, right? Because this is not your field, I guess, for any of you. So the idea is to some general background, some culture about collider physics, particularly on what we do on searches which are related to your field, right? So neutrino double beta decays and things like this. So the idea is really to make this a bit interactive. I guess you're quite tired also. So please feel free to ask questions. I think this is the time. I guess, well, I don't know. Maybe you have 100 different questions about collider physics, what we do at the LHC, things like this. And I will be happy to answer until I don't know what the answer is. And then I will just tell you I don't know. And we can discuss more during coffee break. Okay, so this is the first part. There will be a second part tomorrow. I will come back to this, what I will be describing today, what we'll do tomorrow. First, yeah, just one slide about just my background. So I'm a member of the Atlas collaboration, which is one of the big collaboration at CERN. I will explain you later. So I've been in Atlas for 10 years now, all the way since my PhD, actually. But within, since Atlas is a multi-purpose experiment, you can do many different things and study different sort of physics, and that's what I've been doing. So I did precision measurements in QCD, also searches for new physics, so dark matter, heavy neutrinos. I will discuss that mostly during these two lectures. And most recently, I also measured Higgs properties, okay, and particularly when we produce Higgs bosons in association with top quarks, then you can study the coupling of the Higgs and the top quark. I've also been involved in some different phenomenological studies, also connected to heavy neutrinos. When you're working in the Atlas collaboration, you also do detector calibration, for instance. And recently, I've been heavily involved in the upgrade of Atlas and particularly of the tracking system that we have to replace entirely in a few years. Okay, and then I've been moving to different places, and right now I've been hired at since 2021 I'm permanent physicist at in Paris at CEA-RFU. We also have a group on neutrino double beta decay, by the way, working on Cuore and Cupid. Okay, and I pass by different places. Okay, enough about me. So this is the program. So today, this is meant to be, I hope, really soft for you. Introduction to collider physics, what's important in collider physics, some parameters, some of the variables we use to describe an event topology, these sort of things. Then to give you an overview of a multi-purpose detector at the LHC, because this is what we'll be discussing tomorrow. I mean, results from one of these detectors. And also already to show you the complementarity with lower energy experiments on for a few fields. So there is neutrino double beta decay. There is also dark matter, for instance. So there are a few examples so that you already get some feeling about how collider physics can complement lower energy experiments for different fields actually, and not only on neutrinos. Tomorrow will be of our searches for heavy neutrinos at the LHC, okay, the Large Hadron Collider. Related searches also at LHCb and Bell, so I will discuss that tomorrow. Prospects at future colliders, and also, let's say, a neighboring field, which is the searches for charge, lepton flavor violation at the LHC. Okay, so I put a little meme here. Yeah, don't be shy and just ask questions. That's the good time, I think, for you to ask whatever question you have. It's not even your field, so yeah, just ask what. Okay, so far so good. So let's start with introduction to collider physics. And there is the capital of the world for collider physics is this city. Do you know which city it is? Geneva, yes, exactly. So this is Geneva in Switzerland. Oops, sorry. Where CERN is, okay, so well, my opinion is that it's a bit a boring city, to be honest, but you need to like the mountains. Then if you like the mountains, it's one of the best cities to live, I think. Okay, so testing the standard model with colliders. So the point of a collider is to convert collision energy to mass energy. And then the physics you can do there is driven by the center of mass energy of the collider, okay? That we call square root S, which is a reference to the Mandelstam variable in a 2 to 2. So this is a formula you probably saw before. Then very roughly, because I don't want to discuss this during 15 minutes, you have two sort of colliders. You have the lepton colliders. So the only leptons in practice we can collide are electrons. Okay, maybe one day we'll be able to collide muons, but that's okay. We need at least 30 years, I think. So electrons are elementary particles. So at the end, the processes you get are quite simple, and you have a low background, right? When you collide electrons, you have at first order you have electron processes. The issue of the lepton colliders is that you have a limited center of mass energy due to the Bremsstrahlung. So if you imagine a circular collider, you have to bend the electrons, okay? And the Bremsstrahlung scales as 1 over the mass to the power of 4, and the electrons are light. And then you lose basically a lot of energy when the electrons are circulating, okay? So you cannot go super high in energy. That's one of the strong limitations. Okay, and then you have hadron colliders. So they are much heavier, so you don't have this problem. You can go at much higher energy, so you can increase a lot the square root S, but these are composite particles. So when you collide them at high energy, basically you break them, and this creates a lot of background related to the strong interaction, okay? Then if you go, well, this is just a brief recap of, this is the center of mass energy as a function of the year for different colliders. This is the log scale here. And so it's log scale. Huh? For instance, you have protons, which are in blue. So you see it scales linearly in log scale, which is quite nice to see. And then for the leptons, you see there is like a plateau already due to this feature here, okay? But so to give you an idea, for leptons, we are at the level of less than the TeV, okay, much less than the TeV, whereas for hadrons, the LHC here is at the level of, well, it's 14 TeV in the center of mass. Okay, so just to illustrate this feature of QC background for hadron colliders, low background for lepton colliders, this is what we call an event display. Okay, it's a way to display a collision graphically. Sure. Ah, well, the problem is to have a high quality muon beam because muons are decaying. So you first have to create your muon beam, and the beam, then you want a beam which can be controlled. And the beam is diverging all the time and so on, so you have to refocus it. And to make it work, you need a sufficiently high number of muons. So you need to be able to make some statistics. So for instance, one of the issues is that you get huge fluxes of neutrinos in a muon collider at the level that you don't want them to go up to the surface because it could be an issue for people. So there are a lot of problems actually. It's just to make it possible. Okay, so just if here we are looking at a collision where you have a pair of W boson which get created, okay, and then each of the W boson decay leptonically, okay, so you have basically one electron and one muon that you can observe. If you look at this, so these are the diagrams, so they are very similar between if you do this in electron-positron collisions or in proton-proton collisions, okay? And if you look at this in an electron-positron collision, so for instance at LEP, which was an experiment at CERN in the 90s, then you see basically there is one electron and one muon, and that's it. Okay, nothing else. Super clean. If you look at this at the LHC, where you collide protons, you have one electron, one muon, and then you have all this scrap around, which is basically because the proton breaks. They broke during the collision, and then they're creating a very large number of other pions and things like this. Okay, so this is really what you should have in mind between lepton collider, hadron collider. Okay, two very important parameters when you're doing collider physics. So that's what I wrote. Colliders. So the energy frontiers that I already mentioned. Basically, the square root S, the center of mass energy, it sets the maximum energy available for new particles. One thing to keep in mind, though, is that at hadron colliders, you're resolving the proton structure. So when you collide protons, it's not really the whole proton 1 which interacts with the whole proton 2, but it's actually one proton in proton 1 which is interacting with one proton in proton 2. Okay? And because of the proton-parton density functions, these two partons, they don't have the same energies than the proton, right? They have a lower energy by definition. So what matters at a hadron collider is actually the square root S of the parton which are interacting. And this is probabilistic. These are things we know from other experiments. So this shows you the probability of finding, for instance, a U quark in the proton, a D quark in the proton, etc., depending on the momentum fraction it carries. Right, so at a hadron collider, even if you collide protons at 14 TeV, for instance, the actual center of mass energy of the collision is smaller than that, okay, because the partons are interacting. Okay, the other frontier is what we could call the intensity frontier, and it's connected to the concept of luminosity. So it's basically how many collisions you're making. It's the minimum cross-section one can measure in a collider. So it's typically expressed in a barn to the power minus 1 second to the power minus 1. So it's equal to 1 over the cross-section times the expected event rate you get. Okay, so if you integrate this guy over time, you get the integrated luminosity, and then the formula, which is simple and remind, is that for a given process with a given cross-section, if you multiply these by the integrated luminosity of the data sample you collected at your collider, you get the number of events. Okay, so if I have the total Higgs cross-section from protons is something like some tens of picobarns. So if I have one inverse picobarn of integrated luminosity, I will observe tens of events. Okay, that's what I start from. Then there are detector accident efficiencies, etc. Here I just showed as an example the integrated luminosity at the Large Hadron Collider for the different years. Okay, so I guess the order of magnitude here is interesting. So at the LHC we collect tens of inverse femtobarn of data. So basically we can observe cross sections at the level of the femtobarn. Well, few femtobarns. Okay, one more point. Well, two more points, but this is the first one. So at the LHC, we collide protons. I will explain you a little bit. I mean, I will introduce you the LHC a little bit later. But we collide protons, okay? It's a proton-proton collider. And then one thing to keep in mind, so we collide protons at high energy. So what we have actually are parton-parton interactions. And how the cross sections at the end are given by the product of the partonic cross section. So you compute your cross sections for U quark and D quark or whatever, partonic channels, and then you multiply this by the probability to find that parton inside the proton at that energy. Okay, so this is this formula, this is the partonic cross section for all the possible initial states, and then you have to multiply these by some probabilities which are the proton PDFs which are determined in other kind of colliders. Okay. Right. So at the end of the day, this is a plot that I like, which is as a function of the. This is the center of mass energy, the parton center of mass energy. So if you look at very high energetic collisions, okay, you see that we have actually a very large number of U-quark gluon initial states. Okay, if you look at very low parton center of mass energy, you have a majority of gluon initial states. Okay, because the structure, the proton is a very complicated object, and depending at which energy you look at it, it doesn't have the same quark and gluon content. Okay. Okay, so it's a subtlety that's it's very fundamental at the LHC when you typically if you're a phenomenologist, this will be super important for you. Okay, so I think this time it's one last thing. A bit of, so okay, we collide protons, but then how do we map the event? What are the characteristics of this collision? How do we map the event topology? So we use these sort of coordinates where the beam is circulated along the z-axis. We define the transverse plane, which is this xy plane here. So okay, the one proton goes this way, the other proton goes that way, they collide here. Then we have the transverse plane, where we define the polar angles, the azimuth angle, and so on. Again, since we're colliding at the protons at energies which are far beyond the proton mass, we do parton-parton interactions. Okay, so the rest frame is not the lab frame. When you collide, so two protons collide head-on, so the proton-proton rest frame is the lab frame. But since we collide partons, the parton-parton rest frame is not the lab frame. It's boosted in general along the z-axis with respect to the lab frame. Okay. And this has an interesting consequence. So then you don't know, right? I mean, you don't know the energy of the partons which interact. You don't know how much momentum fraction they carry with respect to the proton. So that's a bit an issue because you don't know your initial state. Okay, so you cannot use momentum conservation along the z-axis. Okay? Along the z-axis, you don't know what's the initial momentum in the lab frame. However, since all the partons are confined inside the proton, you know that their transverse momenta in the initial state is lower than the color confinement scale, which is smaller than 0.5 GeV. So what you can say is that in the initial state, the sum of the transverse momenta, so the transverse momenta is the momentum in the transverse plane, is equal to 0 roughly, because we are talking about tens of or hundreds of GeV particles here. Okay. So by momentum conservation in the final state, momentum is the sum of the momenta of all the particles is equal to 0 in the final state as well. So the practical consequence is that if you look at an event in the transverse plane, like here, so imagine that protons are colliding, perpendicular to that plane, they balance, right? So this is in this event, a Z boson was created. It decays immediately to a pair of electron positrons, and there is also an extra photon which is emitted. And you see that actually they balance very well. Okay, so this is really fundamental. We use this all the time at hadron colliders. But along the longitudinal axis, there we cannot use that. Okay. And that's also a big difference with the lepton colliders, where since there we collide elementary particles, this is not PT here, which is equal to 0, is P, right? So then the kinematics is entirely under our control. All right. Yes, so that's the final thing about collider physics. I don't know if you saw that before. I don't know if you saw this pseudo rapidity eta variable before, right? So we don't use the theta, right? We don't use, sorry, we don't use that angle to measure the angle with respect of a particle with respect to the beam axis. We don't use theta. We use eta, the pseudo rapidity, which is defined like this, but okay. Why do we use this? It's because it's to be able to measure angular distances between particles. Um, we could use delta theta for that, but we use delta eta because eta has the interesting property to be independent from a boost along the z-axis. So it allows us to define a distance, an angular distance between two particles independently from the initial, the boost along the z-axis of the initial state, okay? That you have a cut, when you select your data, you have a cut which is independent from the center of the partonic center of mass. Okay, it doesn't depend on which, because you don't know what it is, right? So you want, when you select your data, you want a cut which is independent from your initial state. And that's how you achieve this. And so that's why we make our life complicated and use eta everywhere. Okay. Then the other thing is what we call the missing transverse momentum. So that's also something you may have heard from. It's very important, particularly in new physics searches. We use this all the time. It's to detect, well, it's an indirect way to detect undetected particles. Since in the transverse plane, we know that the sum of the transverse momenta should be equal to 0 by momentum conservation. If it's not, it means that somehow there is some missing momentum which is coming from undetected particles. If there is only one undetected particle, then we know exactly its transverse momentum. But if there are several, we don't know the sum. Okay, so we are somehow missing degrees of freedom here. Well, there are extra degrees of freedom, I mean, in the kinematics. So it's somehow an indirect, incomplete reconstruction of neutrinos, dark matter particles, and things like this, right? Yeah. Also, it's okay. Sometimes it's called PT miss, ET miss, MET. I mean, all these are the same thing. Okay, so don't be confused. Yes, so to show you an example, so again, that's an event display, so I will be showing a lot of, well, a few of these. This is an example of a collision when searching for invisible Higgs decays. So the Higgs boson is a particle we observed recently, so we're interested to understand if somehow it could not be connected to dark matter, coupled to dark matter as well. And so we are looking for invisible Higgs decays. The diagram would be like this. So you have a quark from proton 1, which interacts with another quark from the other proton. They emit W bosons, which fuse to create a Higgs boson, and then it decays to dark matter particles. So what you expect here are two collimated hadronic jets, because the quark here will be kicked out from the beam pipe and hadronize. Okay, so two hadronic jets and missing transverse momentum. So the event could look like this, where you have, so okay, the collision happens, this is the z-axis here. And so here these cones represent the hadronic jets. Okay, and then if you sum over the PT, you find a very large missing transverse energy of 500 GeV. Okay, so that's quite large. And here you see the angular distance between the two jets is very large. Okay, so that's also typically a cut which is applied. In the selection, we select two jets, very well separated in rapidity, very large momentum. Okay. So okay, for now we haven't found evidence of these sort of events, so don't get too excited. It's probably actually a Z to nu event. Okay, so an event like this. Sorry? Yeah, exactly, in neutrinos. So probably only classic light neutrinos, yes, and not dark particles. Okay. Yeah, actually, there was still one last thing. Sorry, I keep repeating this. Something also which is fundamental when you think about hadron colliders these days is so the hadron colliders they are pushing the energy frontier with the center of mass energy. They're also pushing the intensity frontier, meaning that the luminosity at the LHC, for instance, is super high, right? It has we have never built a collider with such a high luminosity. And it has one consequence of this is pileup. So what is pileup? That's something also maybe you have heard from. It's at the LHC, right? Pileup before was, okay, it existed, but it was really minor. Now at the LHC, this is a major thing. What happens that the proton beam is bunched, right? This is just because of the way we accelerate things. So you have big bags of protons. That's the beam. It's not continuous. And then we cross the beams relatively frequently. So you basically collide 10 billion protons with 10 billion protons. Okay, that's what happens. Most of them go through each other without interacting. But with the current luminosity, we actually have, in average, 60 proton-proton interaction, bunch crossing. And so this has major consequences for your detector. Because usually, one interaction out of these 60 are of interest for the physics we want to do. We are interested in heads-on collisions, right? Like collisions where really a lot of energy has been exchanged so that high particles can be produced, and then we can study them. If they just, exchange a photon or something, we are not interested. So for the detector, it has strong implications because it means you have to reconstruct these 60 different vertices, which are spanning over something like 5 centimeters. Okay, so you need like a super high resolution to be able to resolve this and remove all the particles which originate from vertices that you don't care about. So to show you, to show you again, to illustrate this with an even display, this is the simulation, but okay. So this is a Z to mu mu event. So we produced a Z boson which decays to a pair of muons. This is with a pileup of 2, which means that there are 2 proton-proton interactions. One of them is a Z to mu mu, and the other one is something else. So you see, okay, I don't know if you can see okay, there are some tracks, right? But that's all. But then if you go to 50, it looks like this. And very soon, in a few years from now, we'll go to 200. And that's actually only 150. And you see, now you see particles everywhere. Whereas at the end, the only thing you care about are these 2 muons. Okay, so this is another way to see this. So here is the Z-axis. With a pileup of 65, so I think that's probably also okay. That's a data event actually, and so that's what you see in your tracking system. Okay, if you select all the tracks with an energy above 100 MeV, that's what you see. Okay, so that's a big mess. I don't know if you can see the small points, but there are all the reconstructed vertices. This is something like 5 centimeters here. Yeah. That's a miracle, but yes, I mean, it's very challenging, yes. So the tracking algorithms are, I mean, it's a research field by itself, from hits in your tracking system, how you construct tracks and so on. It's very complicated. Yeah, and due to this, I think what is happening now at Hadron Colliders is that really the tracking system is becoming the most important detector ever due to this, okay? Because if you don't have a tracking system which can reconstruct all this, you cannot do anything. Okay, and that will remain in future Hadron Colliders. For lepton colliders is different. For Hadron Colliders, it's really a key element. But what we do also at the LHC is that we just cut on the transverse momentum of these tracks, right? So because at the end you have one interaction where the proton collided heads on, and the other ones are much lower energy. So you can remove most of these tracks by just cutting on their transverse momentum. And you see, if you ask only the tracks above 5 GeV, you find back your 2 muons, and okay, you have a few others, but it becomes much more manageable. Okay, so that's what we do. And that's what limits, for instance, what Atlas or what the LHC experiments can do, for instance, for B physics, right? When we work at high pileup, it's very difficult to reconstruct individual tracks with low PT just due to this. All right, and this has consequences, and maybe something which is of interest for our topic today is, for instance, the impact of pileup on the resolution of observables we reconstruct, and particularly on the transverse energy resolution. So that's a plot from Atlas, but okay, in CMS we also observe this. That's basically your absolute resolution in GeV on your missing transverse energy measured in events where a Z is created and decays to muons. Okay, well, that's a detail. And you see that with the pileup, which is mu, so this is a number, the average number proton interaction, you see that the resolution is degrading, basically. Okay, so we have to be active, and each time we increase we increase the pileup. I mean, the LHC people say, well, this parameter. We have basically to rework the algorithms to make them more resilient to pileup to mitigate this effect. And at the point where sometimes we have to replace completely the tracking system, and that's what's going to happen in Atlas in a few years. Okay. Right. Yes. Yes, this is true. That's what we are going to do in the next years. Yes, basically, when we'll go from pileup of 50 to pileup of 150, there will be some timing layers. So yeah, so yes, we'll bring some timing information, but it's only part of the story. The main thing is still very high granularity, 1 pixel every 50 micron, uh, many layers, the beam as possible. So you need to resist to very high radiations. Um, this is really the key. Then timing is the future, and it can be useful. Well, is useful definitely. But for instance, timing cannot hold super high radiation damage, so you cannot put timing layers super close by. Um, yeah. Yeah, but that's one of, it's true that one of the main R&D now for tracking detectors, one aspect of it is picosecond timing resolution. Well, tens of picoseconds, I would say, which means that you have a resolution of a few millimeter, basically, just thanks to timing. So CMS have actually a very ambitious timing detector for the next phase, which is called HGCal. So they call this a 5-dimensional calorimeter because you measure X, Y, Z, energy, and time. But it's not for the apps. So it's the region where the timing is most useful because it's a region where you have a lot of tracks. Basically, you use central tracks, so low pseudo rapidity tracks, very high PT tracks to reconstruct vertices. Okay, but then you still have like this huge number of tracks which are much closer to the beam. And these ones, since they are closer to the beam, the resolution, if you extrapolate them back to the interaction point, the resolution on the impact parameter, what we call, is lower. And there, if you add some timing layer, you can distinguish much better between these forward tracks, which originate from your main vertex, and the one originate from another one. So here, timing is super useful, actually. And both Atlas and CMS are putting there. Okay, it's just that CMS has, I think, a more ambitious goal with that AGCal because it's a calorimeter, whereas in Atlas, it's basically a tracking layer. Well, it's 2 tracking layers, but also at the close to the in the end caps, what we call the end caps, so closer to the beam. And the technology is not the same. Also, the detector is not the same. Yeah. Any other question? No? Okay, so that was it for collider physics, really. Key physics goals. So the colliders are high mass particle factories. Okay, that's what we want to do with colliders. Okay, the colliders I'm discussing at least. The crucial parameters are center of mass energy, integrated luminosity. That's basically determine what you can. But there are also other crucial parameters like the nature of colliding particles, leptons, hadrons, running conditions, pileup. And this plays also a very important role about what you can do at the end. The colliders, they improve our understanding of fundamental particles and forces. So this I haven't really discussed, but that's what I will, particularly tomorrow. Uh, with them, you can do precision measurement and test of the standard model. You can also search directly for new physics by checking, for instance, if you produce dark matter particles in your detector, in your collisions, or heavy neutrinos, for instance. And you have a very well-controlled lab environment, okay? So it's not like you're detecting some particles arriving from the sky, which traveled through the universe and to many different medium that you know up to some extent. But what we have is a lab environment, right? We have very good control about what we do, the energy of the incoming particles, etc. And colliders are discovery machines. So okay, now it's the delta t, the time difference between discovery is getting a bit larger, but really there was a time where every 5 years a new particle was observed in a collider. So they are really discovery machines historically. And I hope personally that it will continue to be the case. Some people doubt, but don't. Right, so the last particle which was observed is the Higgs boson in 2012 at the LHC, but before that you had the top quark at the Tevatron, the W and Z boson in the UA experiments at CERN, gluons, JEPSIs. I guess there are other examples, but these are probably the most famous ones. Okay, so now I hope you're all convinced that colliders are great machines. And now I will talk a little bit about the detectors we build at colliders. I don't want to enter too much into the details, but it's also to give you some sort of generic background of how they look like, and then some key results, you know, what sort of physics we do. Right. So first questions, you know what this is? Yes, yes. So it's called the globe. So it's just outside CERN, across the street, exhibition center. So it's in wood. Okay, it was given to CERN. Okay, a bit of history. It was given to CERN in 2004 as a gift from the Swiss Confederation to mark 50 years since the organization foundation. And if you're wondering how it looks inside, it looks like this. So you're a bit in a sci-fi movie from the 70s. It's it's interesting. So if you pass by Geneva, I really encourage you to go there. But also now there is like this big exhibition center which opened a few years ago. So yeah, in Geneva there is not much to do. So I think that's one of the highlights. Okay, so a bit of general introduction about CERN. So what is CERN? So first, a lot of people think that CERN is the place where all the physicists are, right? But this is not true. CERN is a place for engineers and technicians first, right? CERN is a facility, right? CERN is an accelerator complex. That's the first purpose of CERN. So in practice, you meet with a lot of physicists inside, but they are most of them are visitors, right? Or what we call users, right? They're using structure, but they are not employed by CERN. They don't maintain the infrastructure. They don't have the knowledge to build the LHC, things like this, okay? So first, CERN is many things, but it's an accelerator complex first. It supports various experiments at energy levels. So, okay, LHC is the very high energy program, but there are also other things, and because it's not just the LHC, there are many different accelerators for different kind of particles. If we focus on the proton accelerating chain, it all starts in a linear accelerator here, where actually you start from hydrogen, okay? Then you make them capture an electron, so you have negative hydrogen ions, and then you pass them through a foil so that the electrons are removed, and you have protons. Okay, in a nutshell, that's what happens. And then you have an acceleration chain which has been built over the years. So the booster is from the 70s, the proton synchrotron is from the 50s, actually. Okay, it was upgraded. And then you have the super proton synchrotron from the 70s, and then you have the LHC, which is from the 20,000s. And at the end of the day, you have two proton beams circulating in opposite directions at an energy of 7 TeV. Okay, that's how you can get collisions at 14 TeV in the center of mass because you are head-on. Okay, so it looks like, so it's the LHC has is big. Okay, it's 27 kilometers underground. That's a tunnel of the LHC. So that's the performance in terms of luminosity. So you have one proton beam circulating in this direction, the other one in the other direction, and then they cross at 4 different interaction points. So they really change beam pipe if you want. They just cross. And when you cross them, that's where you create collisions, and that's where you build big detectors. So there are 4 interaction points. On 2 of them, you have what we call purpose large detectors, Atlas and CMS. And at 2 others, you have detectors which are more tailored for specific physics. So ALICE for heavy ions, and because you can also collide heavy ions at the LHC, and LHCb to study physics. There are also a number of other small detectors which are further away from the interaction points, studying secondary particles created from interactions. So okay, there are plenty of them. Okay, but there are much smaller scale experiments. Now, yeah, I don't know the time. I should be a bit careful. Ah, yes, great, perfect. Yeah, I have. That's fine. So CMS. Well, I will discuss very briefly Atlas and CMS, the 2 multi-purpose detectors at the LHC. So these are big detectors, and they have many different subsystems. Okay. In a nutshell, you have 3 subsystems. The closest to the beam is a tracker, where charged particles leave heat, where you can reconstruct tracks, okay? And this is in a magnetic field so that you can bend these track particles and reconstruct their momenta. Then you have electronic and hadronic calorimeters, which stop electrons, photons, and then hadrons. And then the only particles escaping, apart from neutrinos and dark matter particles and so on, are muon chambers, okay? Right. Then I put some CMS specificities. So CMS has a particularly strong solenoid field, for instance, of 4 Tesla, which, okay, now maybe it seems a bit small, but at that time when it was built, it was a major thing. But okay. Right, and then there is Atlas. So the main subsystems are the same. And what is, okay, maybe one specificity of Atlas, which is interesting, is that okay, you have these toroids here, which actually create a second magnetic field outside the solenoid, which is here, and which bend the muons in a perpendicular plane with respect to the solenoid. Okay, so it gives you some additional handle on the muon momenta, basically. Okay, and this is quite impressive to see because these toroids are huge, and also they were built by my institute, so that's why I mentioned them. Okay, so these are very large scale. Okay, so Atlas is like 40 meters long and 25 or 30 meters high. So these are very huge detectors. Okay, and so they have all these subsystems. Yes, sure. Yes, yes. Yes, yes. This is correct. So first, because the tracking system costs a lot of money, and if and, and also because if you go to high rapidity, you get closer to the beam in terms of angular distance. So you have the occupancy is much larger. So you will basically you will have particles with lower transverse momentum because they are closer to the beam, but you will have plenty of them. Okay, so you need a super high granularity if you want to. So that's one of the issue. But during the upgrading these detectors, and will extend the tracking acceptance up to 5 actually. So, and usually what happens is that for any in practice, what happens is that to have high quality particles, we ask them to be within 2.5. Okay. we count the rest for missing transverse momentum and all this, but not for, if we want a particle very well reconstructed, we restrict. This is an acceptance cut, basically. Okay. So now looking a bit at how we reconstruct all these particles. So all these systems are made to be able to reconstruct whatever type of particles. Okay. Yeah, except neutrinos and very low interacting particles. So I will not go through these, but just to give you a bit of, so for instance, a muon will basically leave not much energy in any of the detectors, except in the muon chambers there. An electron will leave a track in the tracking system and then be stopped in the electromagnetic calorimeter, etc. Okay, so how it works in practice, in Atlas, each object is seeded by a particular subsystem. So if you want to reconstruct a muon, you start from a track in the muon spectrometer, and then you extrapolate it back to the tracking system, and you check if there is a track associated to it. It works like this. In CMS, they are more evolved in some way. They have a global particle flow reconstruction. So since the beginning, they use from all their subsystems to reconstruct particles. Okay, it's a technical detail, but that's yeah, it's interesting. Okay. Right, and then something to keep in mind maybe is that both Atlas and CMS can achieve excellent performance on standard objects, so for PT above 10 GeV, more or less. Okay, for lower PTs, it's not impossible, but the precision is less good. And typically, calorimeter resolution improves with PT, whereas tracking is the opposite. Okay, so a very high PT particle is straight, so you will not have a lot of resolution on its transverse momentum because it will not be bent so much. Okay, whereas for the calorimeter, it's the opposite. So that's what you can see here. So this is the relative resolution as a function of PT. For instance, for pure tracking objects like the muons, you see that the resolution degrades at high PT, whereas for electrons and hadrons, it improves. Okay, that's what is shown. Also, typically, we have better performances at low pseudo-rapidity than at high pseudo-rapidity, just due to the granularity of the detector and the occupancy. That's what is shown here. This is the identification efficiency for electrons, I think. But okay, it's still quite high, right? This is 80%, this is 65%. Okay, this I will go quite quickly, but I wanted to give you a very brief overview of how we do a data analysis at the LHC. So first, I guess it's quite similar to any high energy physics experiment, but this is to give you an idea. So first, we start by implementing our signal model into a Monte Carlo generator, and we generate events with the same for our background, okay? One subtlety here, which is important, is that we simulate also the running conditions. So the pilot will overlay these events, these proton collisions, with with pile-up events, basically, that we simulate separately, and then we merge, okay? And then we reconstruct also, we perform a full detector simulation. And given the size of Atlas and CMS and all their complexity, this is a major challenge in terms of CPU, all this, okay? So this takes a long time. So if you want to make an analysis, you had better fixing this first, because this can take months to have. Okay, then you're really doing your analysis, so you define a signal region which is enriched in your signal. You do this based on your simulation. More and more, so before, when I started in the field, most of the analysis were just cut-based, right? Cut on observables like PT of the muon in the event, things like this. Now it's more and more, it looks like this. So you use transformer layers of machine learning algorithms and things like that. This is really becoming the standard now, and I have to say that the complexity of the AI-based analysis has rose a lot in the last years. It's quite impressive now what is used. Okay, then for the background, what you do is, so you created your Monte Carlo for background and step one. So you have it and you use the distributions of the background. It free floats the normalization, because typically you can fix this you define other selections in your data which are enriched in this kind of background so that you can fit the normalization very precisely. Usually you achieve a much better precision doing this than just relying on the theoretical uncertainties on the normalization. So that's typically what is being done. So you define what we call these control regions. Okay, that's an example of an analysis where this is a signal region. This is for a search for heavy neutrino, actually, where your signal is peaking at high muon PT. And then you define also control regions for your main backgrounds, okay, WZ production, same sign WW production. And here you see you have quite some statistics to fit the normalization. Okay, and then evaluate all your systematics. So these are usually hundreds of systematics. It's a mix of simulation-based, data-driven systematics. And you include them as nuisance parameters in your likelihood, okay? And then what you do is you compute your likelihood, you test different hypotheses. Okay, is my data standard model-like or not? If it's not, then what is the additional contribution I have? Is that the production of Higgs, for instance, an exotic production of Higgs or heavy neutrinos? And then you derive final results, measurements or exclusion limits in case you observe nothing. Right, and so for that we use likelihood ratios. And if you're interested in a method called TLS, which is a frequentist. And you obtain nice plots like this. So this is a measurement of production of Higgs boson in association with a top quark pair. So this is the red component here after fit. Well, it agrees very well with the standard model. And this is a search for heavy neutrinos where unfortunately we observe no signal, so we set exclusion limits. And okay, this is as a function of the mass of the heavy neutrino and of the mixing of the heavy neutrino with the muon, for instance. Okay, so that's how it looks. Nothing too surprising, I guess. Right, so now this is just to give you an idea of the sort of results, the physics we do with Atlas and CMS. So of course, we are the only, these are the only experiments which can produce Higgs bosons on shell. So large part of the program is just to study the Higgs boson, its properties and so on. So these are all the couplings of the Higgs boson with other particles. After a few years of data, how they evolve over time, also how these measurements evolved over time. It's interesting to see. We can also do electroweak physics, so we measure very precisely a number of die boson cross sections, for instance, WZ, WW, etc., probing for anomalous couplings between vector bosons, which hints for new physics beyond the standard model. So we have like huge summary plots like this. And also exotic searches, so that's what we'll be discussing mostly tomorrow. So high mass resonances, for instance, in the dijet spectrum, heavy neutrino searches, so this is what we'll be discussing, and also, for instance, dark photon. I thought maybe some of you are involved on this sort of model, so dark photon also. So it's not a fair overview of all the physics. There are many results. An idea, Atlas and CMS is about 2,700 up to, and this keeps growing. Okay, so the last part of the talk, with the 20 minutes I have left, which should work. I have 20 minutes, right? Yes. Until 45. Okay, perfect. Then the idea here is a bit to give you to convince you to come tomorrow to my second lecture, basically, to show all these big apparatus, which is first there to create high mass particles, study the Higgs bosons, do all these things. We can actually do many more things than what we originally thought. So, okay, some people thought about it since the beginning, but it's the main program is what I discussed before, right? So, well, what I just shown. So, Higgs physics, electroweak precision measurements, like these sort of things. But we can also do many more things, and actually we are quite competitive, which could make some people nervous eventually. But that's what I will try to show you here, and I will take 2 or 3 examples. How complementary we are with lower energy experiments. So I think, okay. First an interlude, sorry. Do you know what this is? Okay, it's more difficult than the previous images. No, it's not a Roman pot. Yes, it's a quadruple. So, well, it's being built. Okay, so around the LHC, you have different types of different kind of magnets. You have the dipoles to bend the particles, but then you have quadrupoles to refocus the beam, because each time you bend it, okay. Also protons, you know, they're all positively charged, so they tend to diverge. So you have to refocus the beam, and you have to refocus the beam in different planes. So you have actually quadrupoles like this, but also sextupoles and even octopoles, and I think you have duodecapoles as well. Just to refocus the beam in different planes, because when you refocus it in one plane, you tend to defocus it in another plane. So you have a number of different kind of magnets doing this, and these ones are actually special ones. So it's one of the 12 new quadruple magnets for the high luminosity LHC. So this I haven't told you about, but starting from 2030, the LHC, so there will be a major upgrade of the LHC soon, where the idea is to multiply by 20 or 10, let's say, the statistics we acquired now. So to increase a lot its luminosity. So if to push back the intensity frontier. We cannot push back the energy frontier now because we have the ring we have, basically, and that will need more work. But we can actually do a lot more luminosity. But for that, we have to change typically these quadruples. We have to go from 8 to 12 Tesla, and basically, it's a technology change, right? So we cannot use the same alloy than what was used before. It was nobium titanium before, but now we have use tin. So it's a new technology, okay? And so this is one of these new magnets which will be installed. Right. So it was also discuss a bit this high luminosity LHC program. Right. So then coming back to the complementary with lower energy experiments, I think maybe one field where the exercise has been pushed until very far is dark matter searches. This complementarity originates from these three different diagrams. So I guess at least some of you are a bit familiar how we search for dark matter. Maybe some of you are even in this field or nearby. So you have three different ways, okay, roughly speaking. So either you look at dark matter annihilation signals from the sky. So if dark matter is somewhere, it can annihilate into standard model particles that you can detect on a satellite with a telescope embarked on a satellite or on Earth. So these are indirect detection. This is indirect detection. There is also direct detection where you imagine, so since Earth is moving around the sun, there should be like a dark matter wind constantly going through us, okay? So we are constantly into this wind, and the idea is to create an experiment where this wind can interact with a standard model particle into your experiment, okay? So it's like dark matter scattering on particles of your experiment. This is direct detection. And then, so you see, you just flip this diagram each time, okay? And then what you can do is the opposite of indirect detection, where you collide standard model particles until, at an energy which allows you to create some dark matter particles, and you assume that standard model particles and dark matter particles are connected through some sort of mediator particles that you don't know. Okay, and so what we can do at colliders is this one, okay? So this is, okay, I don't know how much I go into the details, but we have to define a benchmark model, right? Because in these low energy experiments, here is really a blob, right? It's the effective theory. They don't really care. Since it's low energy, I mean, they don't really care about what happens here. It all integrates. It's all integrated. But in our case, we actually resolve this thing. So we need some more complicated models, okay? So that's why we have to include this mediator particle. So typically the benchmark we use is a mediator particle, some dark matter particles, and then we need the coupling of the mediator particle to the standard model, to the dark matter. and then the mass of this mediator, etc. Okay, so this we have a 4. This is the width of the mediator. Okay, so mass of the mediator, mass of the dark matter, coupling of the mediator to both worlds, and the width. There is a particular case where the mediator is actually the Higgs boson. And that's the even display I showed you some time ago now, Higgs to invisible decays. Okay, that's just an example of these sort of models. Okay, we have the experiments, and if you look at the final picture, I will not go through the analysis, the data analysis searches, but just show you the results, how it looks like. So you may be familiar how we present these results. So okay, there are only exclusion limits. Okay, we haven't observed dark matter. And usually you present, so what the direct detection experiments do is that they present exclusion limits as a function of the dark matter mass and the dark matter nucleon cross-section, okay? Because on their side, they have like an experiment with some atoms, and they are waiting for the dark matter to scatter through them. And what you can see is this is the limit from the direct detection experiments. And actually, when the dark matter becomes too light, they cannot really see the recoil on their experiments, right? So their sensitivity basically decrease for low mass dark matter. But on our side, it's different. What matters actually is the mediator, right? What we want to create is the mediator. Then we just want the mediator decays to dark matter particles, right? So our sensitivity is much more driven to the mass of the mediator than the mass of the dark matter particles. So actually at low, in this range, okay, I don't know if it's low mass for you, but for us it is. So 1 GeV to 5 GeV. The collider experiments have actually a very interesting sensitivity, which beats typically the direct detection experiments, okay? Yeah, so these are more, okay, these are for different models, but the picture is always the same. So this is the limit from the collider, and this is the limit from the direct detection experiments. However, there is one caveat, is that that I mentioned before, the direct detection experiments are based on effective theory because they are low energy experiments, so they don't care about, this is really a blob for them, right? So they just integrate over this. So they make minimal model assumptions, okay? As soon as that mediator is a few GeV of mass or whatever, they don't care. It all integrates. It cannot be created on its on shell anyway, right? So it's all, whereas in our case, it's not the case, right? So we have to make additional assumptions in our model. So our limits are more model dependent, because if the mediator interacts slightly differently, maybe it will make no difference for the direct detection experiment, but for us it will make a big difference. And so our sensitivity is much more dependent on the model. Okay, but despite this caveat, overall the LHC, if you take a specific model, which is a common specific model, LHC has complementary sensitivity, particularly at low dark matter mass. And what I explain here is basically the same for heavy neutrinos, okay? It's always the same. If you compare to low energy experiments are low energy experiments, so they are more model independent. Neutrinoless double beta decay are very model independent, except the nuclear factors. But apart from that, I think the high energy physics it's all integrated out. But for us, it matters, right? So we need additional assumptions. Okay, yes? Yes? You mean this one? This one? Yeah, I didn't go through which line exactly, this one? Yes, sorry. So there are a few. It's basically, it's basically all these things here. So it's also, but yeah, but we don't have neutrino floors at the colliders. Yeah. You mean where the neutrino floor is here? So- Yes. Yes. So yeah, if you so something I haven't mentioned is that in this model there is actually a nice feature is the mediator connects standard model and dark matter. But at the end you don't need dark matter at all. The mediator is to standard model particles as well, so it can decay to two jets. And so this way you can set super strong limits. But of course, one can argue, where is the dark matter here? You're just looking for a mediator. Who knows if it's connected to dark matter or not, right? But it says that if in this model, since you need a coupling to the standard model just to create the mediator, it means the mediator necessarily will also decay to standard model particles. Then it depends on the ratio of the two couplings, how you tune them, okay? So that's why here dijet it's a flat line, right? But for instance, ET miss plus X, where you're looking for missing transverse energy. Well, here ET miss plus X means these are really analyses where you're looking for a mediator decaying to dark matter particles. And here your sensitivity is mostly at low mass. Okay, then at some point it stops. Just because if the dark matter mass is too high, you need a mediator mass super high so that it's not forbidden kinematically to decay to these dark matter particles. Okay, so that's why if you do this, you have like at some point a sharp cutoff. You need to increase your center of mass energy if you want to be able to create this mediator and to extend, to push this boundary here. Okay? And of course, on our side, we don't cast our limits in this plane because for us it doesn't really make sense, but we recast our limits into this plane to compare directly with the direct detection limits. And that's also something very general. So you will see for heavy neutrinos, it's actually a bit simpler. But for instance, if you want to compare our sensitivity to heavy neutrinos to the neutrino-less double beta decay sensitivity, it's not straightforward. You need to go to see a phenomenologist, and he's doing the computation. Yeah, it's a common feature. I mean, we cast our limits into what is most natural for us, but then if you want to do the conversion, you need some tools, right, to be able to do this. Yeah. Okay. Any other question? Yeah, so I think dark matter is really the field where that exercise was pushed a lot because benchmarks were defined in agreement with all the communities, and there is really these plots are accepted by all communities. It's really nice, I think, to be able to show this. But there are other areas. For instance, the left-right symmetric model. I don't know if you're familiar with this sort of model. So the idea is to explain the broken parity symmetry of the weak interaction in the standard model by introducing another W boson, which would couple to right-handed particles, but which would leave at much higher mass. Then overall, before symmetry breaking, then parity is restored. That W boson, it's also created through a Drell-Yan process, like the one we know. It's just much mass, and then it can decay to a heavy neutrino. Okay, so it's basically a UV complete. Well, it's a family of models. I'm not an expert. It's a family of models mixing type 1 and type 2 CISO mechanisms, basically, which allows you to explain, to introduce neutrinos, you restore parity, and so on. So basically, you have these WR bosons. You also have heavy neutrinos that we'll call tomorrow heavy neutral leptons. You also have actually a ZR boson. You also have additional scalars if you do the full exercise. But okay, for the benchmark we want to look at here, you have a WR boson, a ZR, and one heavy neutrino, and that's it, okay? So you have the coupling to the right-handed particles in terms of model parameters. the mass of the WR, the mass of the ZR, and the mass of the of the neutrino. Okay, that's all. Um, right. And so this WR is produced from a Drell-Yan process, so one quark from proton 1, one other quark from proton 2, and it can then decays back again to the same quarks. So you look at dijet events, what we call dijet events. But it can also decay leptonically to a heavy neutrino, which then would decay back to a WR and a lepton. So here you have a more complicated final state that we'll discuss a bit more tomorrow, actually. But the point I want to mention here is that the neutrinoless double beta decay experiments also do have some sensitivity to these sort of models. Of course, the WR is not created on shell, okay? So this is a blob for neutrinoless double beta decay experiments, but there is also some sensitivity. And if you, so some people did that exercise comparing the sensitivity of Atlas CMS for these models and the neutrinoless double beta decay. So I have to say the results for Atlas and CMS here are quite outdated. Now we push, it's much more extending into this direction. But you see, again, there is quite some nice complementarity. So if you go to low WR mass, you start losing sensitivity for Atlas and CMS because the background gets super large, okay? Also, if you want to go beyond that, so that line, so sorry, I should have, let me start again. So this is the mass of the WR, okay? This is a parameter space, okay? Mass of the WR, mass of the heavy neutrino. Above that line, the heavy neutrino is is heavier than the WR, okay? So basically, it's very hard for the WR cannot decay to the heavy neutrino, okay? So this channel is completely off, okay? Whereas for neutrinoless double beta decay experiment, you don't care, okay? Because everything is virtual anyway. You have the sensitivity to probe this. But then the sensitivity of Atlas and CMS is basically stopping here by definition, some sort of. Okay, the caveat is that you still have that channel, okay? And then the neutrinoless double beta decay is different. So it's more that at high WR, then you start to become way too off shell, and then basically your cross section is dying, okay? So yeah, so I think it's another area where there is clear complementarity between the two experiments. So of course, this you mean for in Atlas and CMS? It's this. So you create a WR on shell, which decays to a heavy neutrino and a lepton, and the heavy neutrino decays back to a well, of shell. Well, let's say it's the WR here is off shell, so it's a 3-body decay of the heavy neutrino directly. Okay, so your signature is 2 lepton with the same sign plus 2 jets. Yeah, that's a signature we'll discuss more in detail tomorrow. Basically, it's a fundamental signature when you want to look for heavy neutrinos in Atlas or CMS. But there are also this signature, which is just a dijet resonance. You're looking for a bump because this will hadronize and create a collimated jet of hadrons, same here. And then you're looking at the mass spectrum of events with 2 jets, and you're looking for a bump, which would correspond to the mass of the WR. Yeah, today I decided not to enter into the details of the analysis, but tomorrow we'll really study more in details the signatures and how it looks like in our detector, what are the backgrounds, things like this. Right, and so these are the limits. So basically the green area is from this, so it cannot go above that line because otherwise you close completely your phase space. But for dijets and dileptons, you cover actually that phase space. But then again, one can wonder, you see a high mass, you see a resonance in the dijet or the dilepton spectrum, but it has nothing to do with a WR. I mean, this is just a resonance, right? So it tells you that you're the heavy neutrino. I mean, it's it could be anything, right? So it's more indirect, if you want. If you really want a direct probe, it's the green It's the green areas. Okay, last example, the type 1 CISO. So I guess I've been told that now you're experts on, on this model. You know exactly how it works. So that's why I didn't put anything here. But yeah, basically at the LHC again tomorrow we'll go through this, but uh, it's basically we can look for heavy neutrinos the same way we look for these things, except that it's not a WR here. WR here is just a W, okay? Because we and they can just decay to heavy neutrinos as well as light neutrinos. Anyway, and here it's interesting because it's not only colliders and neutrinoless double beta decay experiments, it's actually a bunch of experiments, and the big picture looks like this. So this is the mass of the heavy neutrino. So this is an exclusion plane, okay? This is the mass of the heavy neutrino, and this is the mixing square with, for instance, electrons, between the heavy neutrino and electrons, okay? And the picture, but okay, for muons and taus, I will also show you the same plot, and the picture is schematically the same. Colliders cover the phase space, the parameter space above few GeV, and above 10 GeV, it's the only one. There are no other experiments up to date which can probe that parameter space. Then if you go lower, you have fixed target experiments, charm, and B mesons factories. And then you have pions and kaon experiments. Okay? Okay, so I will not go through all the experiments here, but basically LS and CMS are here, as expected from this diagram. And here, neutrinoless double beta decay also sets some indirect limits, right? Which would be actually a flat line at, okay, if I'm not making a mistake, between 10 to the power minus 6, 10 to the power minus 8, so something around here. Okay, so actually better than Atlas and CMS. But one caveat here is you could imagine a super complex model where you have no signal in a neutrinoless double beta decay experiment because, for instance, you have more than one heavy neutrino and the diagrams, they interfere destructively or something like this. Whereas in Atlas and CMS, since you're producing all these guys on shell, you can actually study them in different channels and disentangle all these different contributions. Okay, so very roughly explained, but that explains why it's worth looking for things directly as well as indirectly. Okay, so that's for electrons, but then also if you look at muons, here neutrinoless double beta decay experiments have no sensitivity at all, right? So if the heavy neutrino only with muons, you don't see it in a neutrinoless double beta decay experiment. Whereas in Atlas and CMS, you can probe it.
Setting higher and higher limits on the
Mm-hmm.
which corresponds to light neutrino majorana masses, which are smaller and smaller,
Mm-hmm.
which in CISO roughly corresponds to heavy neutrinos, which are
heavier and heavier. Yes.
Why do you say that the standard would have flat sensitivity to MN, would cover MN flat instead of
well, okay, I think it probably depends. That's a good question. Okay, in my view, it was more that when you gain in precision, you go lower and lower in mixing. If you imagine, so it depends a bit how you see it. So if you think that you're probing the diagram with the light neutrinos, here it's a light neutrino, and then you assume some CISO mechanism, so you put some theory assumptions, then I agree with you, to scale with the mass, or like the mixing should enter the game as well, so it's probably, I don't know, the ratio between the max of the mixing. Yes, something like this. Yeah, but that assumes also, yes, I think so. Yeah, exactly. I think so. But you also have the diagram with the, yeah, exactly. I think, yeah, but to be honest, I'm not an expert, and these limits is not derived by an experimentalist. This can be found in some theory paper actually of people. They consider a couple of diagrams and then they do the computation. Um, but you're right. There's probably a slope. It's probably not a flat line, but there's probably a slope. But anyway, it's more I mean, it's orders of magnitude lower than what we can do in Atlas and CMS. Whereas for muons, here there is no neutrino double-beta decay experiment. Well, there are actually other indirect limits, but that we'll discuss tomorrow, which are not shown here. But okay. And then for taus, yeah, for taus, you see actually they are this plot is much less busy, so there is actually quite some room for new physics here, and that's something that CMS is trying to tackle. So here you see only Delphi, which was a LEP experiment, but actually there is a new result from CMS, which is around here, and which actually extends the sensitivity above the Z mass. So there is some sensitivity from CMS here, which is not shown. But you see the mixing. We cannot go very low in mixing. Okay, and I don't think that's something we can address by tomorrow. Okay, so here as well you have nice complementarity between different kind of experiments, and it's very nice to see all these pieces of the puzzle going together to get this big picture. Yeah. Okay. Last question. Can you see this sign here? I don't. Do you know what it means? Maybe if some of you work underground in some of your experiments, you also have it actually.
Have you taken safety courses anywhere?
Yeah. So what is this? Can you see it? It's like a guy who is sitting on the ground with the head like this. Nobody? Are you guys working underground with argon and I don't know helium and stuff like that? No, none of you? Okay.
Asphyxia.
Yes, it's called anoxia, lack of oxygen. Yes, but that's basically it, yes. So when you're in a confined space with large quantities of cryogenic fluids, and if you have a leak, basically, you have a risk of anoxia because if the gas just expand, suddenly you cannot breathe anymore. And that's the case at the LHC because the LHC is using superconducting magnets, and so there is a lot of liquid helium flowing around, which is essential for cooling because it's cooled down to 1.9 Kelvin. Right, so you have these these panels actually with a big alarm here. So if this turned on, you have to run. Actually, I think there is a special mask to deal with it. It really looks like you look like Darth Vader when you have it. It's wild to wear it, so I don't know how quickly you can be fast enough to put it on before you die. But that's another yeah, that's another story. Yes, and that's the LHC tunnel. So people actually use a scooter to. I mean, so they are usually physicists don't go there because I guess yeah, reasonable people want things to work, so they don't want physicists in there. But it's mostly engineers and technicians, and they use 27 kilometers long, right? So there are different access points, but sometimes you have to make case to go where where you need to go. Yeah. Anyway, right. So this is my last slide with a short summary. Also, I realized a bit late that I didn't show you any pictures of these huge detectors. So I put one here. I don't know if you see the scale. This is Atlas. This is one of the toroid magnet I told you on the outer part. And here is just I mean, what we call the end caps, which are pushed away. If you want to open Atlas, this takes weeks, right? It's not something like, okay, we want to change something here. Let's just open and change a couple of cables. This takes weeks because the cavern has approximately the same dimension than the detector. So you don't have much space. When you visit, you have the detector is here, right? And you're like, oh, okay. And so just to move things around is complicated. Anyway, so I just did that picture a bit late. I have others if you're interested. Also online, you can find plenty. Okay, so 3 bullets to finish. So what I mentioned at the very beginning and try to convince you. So colliders improve our understanding of fundamental particles and forces. You can do many things, precision measurements. You can measure the W mass at the level of 10 MeV precision. But you can also set competitive limits on dark matter production and particles. So that both direct searches for new physics and precision measurements. We have a unique environment which is super well controlled. We don't rely on the strength of the dark matter wind hitting us. We don't rely on, well, on nuclear factors. I guess we rely on proton PDS, but okay, that's maybe not the best example, but it's a very well controlled lab environment where you can perform measurements dedicated for calibration, and that's big part of the work. If you want, you know, the electron efficiency, we derive these from data. Well, that's standard, I guess, but like a very well controlled environment to do all these supporting measurements as well. So we can reach sub-percent precision on identification efficiency of electrons, muons, whatever. Then, so right now, the big machine in function is the LHC at CERN, and on that machine you have Atlas and CMS, which are the two multi-purpose detectors. We'll discuss a little bit about LHCb tomorrow because it's also, they are doing interesting things for heavy neutrinos as well. But these ones are really the two multi-purpose large-scale particle detectors, and they have a very wide physics program. So I'll give you a very quick glance, but yeah, that's to give you an idea. And I try also to illustrate the complementarity with lower experiments, which was explored in details for dark matter, but they also exist for the neutrino sector, left-right symmetric model, CISO, and we'll discuss that a bit more in detail tomorrow. Thank you.